A ball rolling off a table. Here's the question. A ball rolls off a 1.5 meter tall horizontal table and lands on the floor zero point 0.7 meters away. How much time is the ball in the air? How does that time compare with the time it takes for a dropped ball to fall that same distance? What is the ball's velocity while it was on the tabletop? What is the horizontal component of its velocity just prior to impact? What is the vertical component of its velocity just prior to impact? What is the magnitude of its velocity just prior to impact? And what is the direction of its velocity just prior to impact? The first step of a lot of projectile motion problems is going to be to find airtime. Airtime might be a given in the problem, but a lot of the times you are going to have to find airtime. To find airtime, we're going to use the second kinematics equation in the y dimension. And that's because that's the only equation we have that has time in it, that we have all the other givens that we need. So for example, here's our list of givens. And because this is a horizontal projectile, the ball is going this way, its initial velocity is 100% in the x dimension, which means the initial velocity's y component is 0. And so this term goes away. Our final y position is the floor, right? Because we're going to land on the floor. So that's 0 as well. We have our starting height, which is y naught, which is 1.5. And we know the acceleration in the y dimension, because for all projectiles near the surface of Earth, that's negative 9.8. So this is the equation we have where we have enough information to find airtime. We solve this equation algebraically for time. We get the square root of 2 y naught over g, plug in our givens, and we see that the ball is in the air for 0.55 seconds. How does that time compare with the time it takes for a dropped ball to fall that same distance? The first ball rolls horizontally, so here's our table. The first ball rolls horizontally off the table and lands over here. Not quite like that, but you get the image. While the second ball, same height, but it is dropped, meaning it was released from rest. Therefore, the vertical component of the velocity, so the y component of their velocities, both 0. And because the balls start from the same height above the ground, they have the same initial vertical component of velocity, and since air resistance is negligible, both balls undergo the same constant acceleration due to gravity. Therefore, the two balls take the same amount of time to reach the ground. The times are the same. Just see here, remember the dimensions are separate. So just because the first ball has horizontal velocity, it's still accelerating towards Earth at 9.8 meters per second squared, along with the dropped ball. If there was no gravity, this first ball would just keep going straight this way forever. So the time it takes both of these balls to vertically accelerate towards the ground, it's going to be the same time. What's the ball's velocity while it was on the tabletop? Because air resistance is negligible, after the ball leaves the tabletop, the acceleration in the horizontal direction is 0, meaning the ball travels with a constant horizontal velocity. Since the horizontal velocity of the ball remains constant, we're going to apply the second kinematics equation in the x direction and solve for v naught x, the initial horizontal component of velocity, which is the velocity of the ball on the tabletop. Alright, so here's our picture. The ball lands over here. Our initial position we'll say is 0. Our final position is 0.7 meters. And I'm just looking in the x dimension right now. We don't have any acceleration in the x dimension because there's no forces acting in the x dimension. So this term goes away. And because x naught is 0, that term also goes away. And what are we left with? Distance equals speed times time, right? How far you go in the x dimension is just how fast are you going and for how long, which is why we need that air time. Anyway, we already know how far away we land. What we're looking for is the initial velocity off the table. So we're going to rearrange this equation to solve for v naught x. So speed is distance over time. We go 0.7 meters in 0.55 seconds. Therefore, that x component of velocity is 1.3 meters per second. Just prior to impact, the horizontal component of velocity will still be 1.3 meters per second, since there's no horizontal acceleration of the ball. So in our picture, as the ball falls down, I'll draw little velocity vectors. In the x dimension, there's no forces. So therefore, there's no acceleration. There's no change in velocity. The x component remains constant through the entire flight. However, the vertical component of velocity does change through the flight. So if I draw my picture, and there's our flight, the horizontal components stayed constant, but vertically, there is none to begin with. Then we're going to be changing our velocity by 9.8 meters per second every second. Right? We're speeding up towards the ground with an acceleration of negative 9.8 meters per second squared. So use the first kinematics equation in the y direction to calculate the vertical component of velocity just prior to impact. Set up the variables to start at the moment the ball leaves the table to the moment it hits the ground. Since the ball is rolled off horizontally, the initial vertical velocity is 0. And we already calculated the total amount of time that the ball is in the air. So the ball is accelerating from rest for 0.55 seconds at a rate of negative 9.8 meters per second squared, giving us a final vertical component of velocity of negative 5.4 meters per second. What is the magnitude of its velocity just prior to impact? So what's the total speed of the ball right before it hits the floor? Well, we already figured out the two components of the velocity. There's two components which must be considered, the horizontal and vertical. And we already figured them both out. The horizontal was constant for the whole flight at 1.3 meters per second. And we just calculated that the final vertical velocity was negative 5.4 meters per second. So in order to figure out the total speed, we need to find the length of the hypotenuse. We're going to add those vectors together and find the resultant vector. So we need to use Pythagorean theorem. This side is 1.3, that side is 5.4. The length of the hypotenuse is 5.6 meters per second. Finally, what is the direction of its velocity just prior to impact? When solving for velocity, a sketch can be helpful, in addition to using these equations. So here we have our vectors. We know the horizontal velocity was 1.3 meters per second. We know the vertical velocity is negative 5.4 meters per second. This is two-dimensional, right? This total velocity, it's two-dimensional. So in order to have a direction, we need to include the angle. So this angle here, that's what we're looking for. Because we have the two sides of the right triangle, let's use inverse tan. So inverse tan of theta is opposite over adjacent. So that's negative 5.4 divided by 1.3, and we take the inverse tan of it. And we see that this angle is 76 degrees below the horizontal. That's what that negative sign means here.